Today I want to talk about our current work on clinically grounded machine learning. This is mainly joint work with Aalto University and Salma Rachidi, who is currently also with the Helsinki University Hospital, HUS. And yeah, this work is funded also by a current Research Council Finland project on trustworthy AI. Okay, so without further ado, here is the main question, or the guiding research question for this work is, what is a simple and efficient way to incorporate clinical knowledge into machine learning models? So how can we most easily bring in domain expertise from doctors or clinicians who work with patients, who study clinical trials, and then publish papers? So this knowledge is available in the form of publications. How can we bring that in the easiest but efficient way into machine learning? And yeah, the motivation for this work is, of course, the nature of healthcare applications. So they are typically high stakes, and we have limited resources, which means the decisions, they should be accurate. So they should be optimal in some sense. And nowadays we also require interpretability. So there are now some regulations regarding the European Union AI Act, or also regarding special agencies for medical devices or drugs, here the Food and Drug Administration, that specifically demand explainability. So I would like to highlight this right to explanation of individual decision making. So some of you might have read already the European Union AI Act. But for those who didn't yet, I have here a quote of the relevant Article 86, which says, any affected person shall have the right to obtain from the deployer clear and meaningful explanations of the role of the AI system in the decision-making procedure and the main elements of the decision taken. Any comments or questions so far? I would like to have this meeting as interactive as possible. So please, if you have any comments, just raise your voice or put them in the chat. So this is nice, of course, to have the right to explanation of individual decision making. But there seems to be little consensus on what a good explanation is, or what a suitable explanation is. So there are very few court cases. I only know one where there's a reference to a particular type of explanation. And one of our main foci is to develop such precise notions of explanations or explainability. So how can we measure the usefulness or the quality of an explanation? Yeah, but this requiring explanations might seem a hindrance. So there are a lot of critical debates that that the European Union is regulating too much. So we're requiring too much from AI companies. But our view, or my view at least, is that it's not a hindrance. It's actually a good thing. So we will use explainability or interpretability to make machine learning better. So does anyone have problems? Can you hear me properly and see my slides? There was one comment.
Yes.
Yes, everything
okay.
is clear.
Okay, So we view explainability as a useful design requirement, which also leads to improved accuracy. So it's not we do not see also in our experiments we do not see a hard trade-off or a clear trade-off. So when you require more explanations, you get less accuracy, but the opposite. When you require more explainability or interpretability, in particular interpretability for clinical experts, for clinicians, then this is typically helping the model training. It's a form of regularizations. And the core idea is that we require machine learning predictions to be consistent for clinically similar patients. But then, of course, you might wonder what are clinically similar patients. Is there any comments? Yeah, please mute your mics if you don't want to ask questions, or otherwise we have some interference here. So what are clinically similar patients? Well, we have a few ways to define clinical similarity. I mean, the ultimate way would be to ask a clinician, look at this patient, look at that patient, are they too similar? But for this, you need a clinician. And you not always have a clinician around. Their work time, they are costly, they have a high hourly rate. So what other sources could we use for clinical similarity? Well, we could use predictive features. So just recently, 2 days ago, I heard in radio, in general news, there was a new discovery of a predictive feature for cardiovascular diseases. Maybe some of you have heard about this too. It's about a certain lipoprotein, which they found out to be really important for predicting the cardiovascular risk, or the risk of cardiovascular diseases like strokes. So for some diseases, we know what the important features are of a data point being a patient. So I have just researched here for three diseases: stroke, for example. It seems that hypertension, so the high blood pressure is a strong indicator, and this has been found so this knowledge is available in publications. What I said before, the source of clinical knowledge for me is literature, is papers in clinical journals. And according to this knowledge, hypertension is an important feature for stroke. For diabetes, an important feature is the body mass index or obesity indicators. And for lung cancer, it's the fact if you are smoking or not, which seems natural to me. Okay, so one way to define this notion of clinical similarity is by looking at these key factors. So you would say, regarding stroke or the risk of having a stroke, you consider two patients similar if they have hypertension, or they are similar if they are not having hypertension, if they have low blood pressure values. So this is one way to get a notion of similarity via this key features. I call this key features. Yeah, and here's this example that I alluded to before, which I learned about actually not via research, or well, basically it's also part of my research to listen to public media. And in the public media, there was 2 days ago this piece about a new work that studies the relevance of a particular protein or new blood value that is useful for preventing cardiovascular diseases. This is called LPA. I don't know any details about this because I'm not a clinician. However, I am machine learning scientist. So what I could do is then, of course, find data sets where these LPE values are available for patients and try to learn a model. So I can then try to learn a simple model, which is shown here. This G of X is a simple model that, for example, only depends on this LPA value, very simple model. And I could use this simple model to guide the training or to regularize the training of this high dimensional model, and a nonlinear model. For example, what's your favorite nonlinear model at the moment?
Neural network.
A neural network, yeah. What type of neural network is at the moment very fashionable?
Perceptron.
Perceptron, yeah, perceptron is already quite traditional, but very much at the moment in the media, in the context
Um, it's a convolutional neural network.
convolutional neural networks or transformers. Yes, so in the context of text, it turned out that these transformer networks, which are based on something called attention or self-attention uh, modules or units, turns out to be useful, but might change. Who knows what the next fashion wave will bring? And so you take whatever current super powerful high dimensional model you have, and what will happen in practice or often is you have too little training data for these high dimensional models, which have billions of parameters, which would require, roughly speaking, billions of training data points, each data point being a patient. And ideally, you would have these patients in a clinical trial. So show me one clinical trial with a billion of participants. Uh, Maybe there is, but I'm not aware of. As I understand, these clinical trials are very expensive and don't have billions of participants. So what instead we could do is we could use this highly concentrated knowledge available in clinical literature, and extract this knowledge to train this simple model. For example, using this one important features LPA lipoprotein value to predict stroke risk. And this might be too simple in general because it only uses one or two or three important features, but it's not personal. There might be other factors like your lifestyle if you develop a stroke. If you're working in a very stressful work, then you should also take this into account. And there comes then this high dimensional models into play, which can use more aspects of a patient. And so our work, the key focus of this work, of this line of work, is how do we combine these two worlds? How do we get the best out of both uh, approaches? The old-fashioned clinical approach, using on a few well-chosen features, and the new, in some sense, dumb approach, which just feeds tons of data into a large dimensional model. And we combine those by requiring the high dimensional model to not deviate too much from this clinical or clinical grounded model. And by this, we kind of blend those two worlds. We blend this high dimensional model, which is at risk of overfitting, with this well understood, interpretable low dimensional model, which might not be able to catch all the details of an individual patient to give a personalized risk prediction. Okay, so I mentioned this key features as one way to get the notion of clinical similarity. Another widely used technique for clinical similarity is called staging. So has any one of you heard about staging systems? If you know about cancer treatments, then maybe you know already there are different stages, cancer stages, for example. But there are also other similar staging or classification systems that I just found in the literature. For diabetes, we have three different stages: normal, pre-diabetes, and diabetes. For strokes, stroke scales, there are different scales for strokes, and these are essentially uh, grouping or classification systems which tell you these two patients are in the same class. So it's a more discrete form of similarity, whereas if you use features, you have a more continuous form of clinical similarity, and this is a more discrete form of similarity. So either two patients are similar or not, either they are in the same scale or not. Okay, so how do we then use this? So how do we implement this idea that I talked about before? Well, in the end, it's a form of regularized empirical risk minimization. As often, in applied machine learning, the crucial thing is how do you regularize the training of a high-dimensional model. Training a high-dimensional model is nowadays pretty convenient because you just specify a loss function, squared error loss or cross entropy loss if it's classification, and then you optimize this training error, or you minimize this training error by using gradient descent or some variant of gradient descent. But this might typically result in overfitting since you don't have enough training data for high-dimensional models to fit them directly. So you need a regularization. You need to regularize the training. And this is the hard part in applied machine learning, to come up with this regularization term. And in this work, we use a regularization term that measures the interpretability in a sense. In particular, we construct this regularization term via the variability of the predictions that we obtain from the model H across clinically similar patients. So we want to learn a hypothesis. We want to learn a predictor for stroke risk that delivers similar predictions for clinically similar patients. And this regularization parameter alpha here controls the level of interpretability. So if we choose alpha very large, we really want to have a very interpretable model, so to say, that very much agrees with clinical knowledge. So it delivers exactly the same predictions for patients in the same category or class, which comes at the cost of personalization, of course. So you treat everybody in the same cancer stage identically, which might not be useful or might not be the best way regarding accuracy. So that's why we typically don't choose alpha too large. Yes, and then in our work, we look at two specific constructions for this regularizer, which are based on these different forms of clinical knowledge. So this first construction uses key features of data points or patients. And then we use these key features, these few features, to train a low-dimensional model. Roughly speaking, the number of data points corresponds to the number of features you use. At least for linear models, you can use this rule of thumb without too much headache. So if you use only few key features, you can train a linear model on a rather small cohort or small data set. Okay. And once we have this clinically grounded model, G of X, which could be, as I said, a linear model, logistic regression, a linear classifier, for example, we can use it to measure the discrepancy between this simple model and the predictions of the high-dimensional model. And yeah, that's then what we use as regularization term, these discrepancies. And the discrepancy measure differs for different types or structures of the label values. If these predictions are numbers, numeric quantities, then we could use here squared error loss. But if they are classes, so you want to predict survival, will the patient survive the next 5 years, yes or no? So these are binary, then you should use a different loss function, like a binary, like a cross entropy loss. Okay, and the second construction is based on a staging system. So whenever you have a staging system, which allows you to group patients into stages, into a few stages. Let's say we have capital S stages. Each patient belongs to one of these capital S stages. Then we can use the variation or the variance, the empirical variance of the predictions, if this is a numeric quantity. So this works if it's a numeric quantity. We can use this variation in each stage as a measure for lack of interpretability. So the more this high-dimensional model varies for patients in the same stage, so it delivers very different predictions for patients that belong to the same stage, then we could consider it as not interpretable or not clinically grounded. So we penalize these variations. Okay, any questions so far? Yeah, if not, then I briefly present the case study that we used, or that Salma used mainly in her master thesis, which was cancer survival prediction. So the data points here are patients which have been diagnosed with multiple myeloma. And these patients have been diagnosed and treated at the Helsinki University Hospital, HUS. Uh, and as features, key features, or as features, we use the age and blood values or blood biomarkers. And the quantity we would like to predict is the 5-year survival outcome. So will the patient survive the next 5 years after diagnosis or not? Okay. Yeah, and then given all these characteristics, we or Salma trained an artificial neural network using this regular interpretability regularizer, and then studied what is the resulting prediction accuracy on a test set. So how often, or what's the rate of correctly predicting the 5-year survival? And she also measured the explainability by comparing the predictions of the high dimensional model with the predictions of the low dimensional model. So this is a measure for explainability. And what she found was that if you increase alpha, so if you increase the level of interpretability, or in this case also explainability is a special case of interpretability, you also can improve the accuracy. You also can improve the statistical or the predictive performance of the model. So here's one example of a win-win, so to say. So if you increase interpretability, or you increase the required interpretability of the trained machine learning model, you also help the machine learning model to learn better predictions. So it's not interpretability versus accuracy, it's use or leverage interpretability to improve accuracy of machine learning models. Okay, so that already leads me to the end of my short talk. So the takeaway of this work so far is that we construct regularizers that capture clinical knowledge. So either clinical knowledge in the form of key features like blood pressure values for predicting the risk of strokes, uh, or what else? Certain blood biomarkers for predicting survival of cancer patients. And then we also use another construction of regularizer, which is based on staging systems. So we use clinical knowledge in the form of staging systems to ensure interpretability of machine learning models. And yeah, this regularizer, or the value of this regularizer, can be interpreted as a measure of interpretability. That's a funny phrasing, I must admit. But yeah, this is one way how you can actually compute interpretability, or the level of interpretability. We have here a formula. And you can compute this. You get a number out of it, and this number then tells you, is it more interpretable or less interpretable? So this might be one way to standardize measuring interpretability and use these measures in court cases when some patient challenges the decision of a healthcare provider. Because this decision or this prediction of a healthcare provider might result in allocating costly resources like a surgery, which is very costly, to a patient or not. And this can be a matter of life and death. Yeah, here's a question. Did the doctors at HUS, at the university hospital, take the model acceptable as accurate and interpretable? Yeah, that's a good question. As I said, there is no consensus yet. What is an interpretable model? So, what a clinician would do is, I guess, look at these key features or just determine the stage. So you just categorize patients. And that's how you get then a prediction of the survival. So there are then this, how is this called? Kaplan-Meier plots, which shows you a distribution of what's the average survival rate of stage one patients or stage two patients. So the interpretability so far is, or interpretable clinically interpretations amounts to finding out the stages. But I'm not aware, so I didn't learn yet a widely agreed upon measure of interpretability for a general purpose machine learning model. Like you use your favorite transformer networks, why not, and train it on healthcare records. How do you measure the interpretability of those? Okay. What else in the takeaway? Yeah, it's important that you see interpretability not as a hindrance, but as a form of regularization. And this can be good, this can be useful. So higher interpretability can result in higher accuracy. I also want to highlight that this notion of interpretability and explainability is subjective. So when I talk about interpretability, I should always specify for whom. For whom should this be interpretable? For me, telling the lipoprotein values of a patient as a explanation for a prediction or risk assessment is not very useful. For a clinician, it might be. So you always need to specify, you always need to target or tailor the interpretability to a certain user or user group. And in our case, the user group are clinicians. In our case, the user group are the, for example, the authors of these papers. For them, our approach is interpretable, but not maybe for example, for me, when I'm as a machine learning scientist, go to whose lab for a treatment. So for me, it might not be interpretable. Sorry. Any questions so far?
Can I have a comment?
Yes, please.
I was thinking like about like these notions of I mean this is a very nice idea how to formalize this and using this G function that defines somehow this interpretability part for us. And then I was thinking whether we can also consider using human in the loop kind of approach like reinforcement learning with human feedbacks when you learn or something similar to that when you learn these values by interacting with human. And then so one way is like yeah we can look at the papers and find out this discriminating features or important features, but then maybe also it's learnable by interacting with humans as well. mm, yeah, so
So
just
how
wanted
how
to.
how would this interaction be implemented? The human would say good prediction, bad prediction.
For instance, yes, or yeah.
Yeah,
We can have different types of feedbacks, and then, for instance, it could be that, um, yeah, for instance, if you're trying to find like, are they similar? And then we show the two to the human, and then ask, are they similar, or how, or not,
yeah.
or something like that, and then learn a function based on the feedback that like this function based on the feedback that we receive from
Mhm,
human.
mhm. Yes, I mean that's very much similar. That's very similar in my opinion. It's just the difference would be in how you compute, how you optimize, how you solve this optimization problem, or also the loss function. So you would not have a loss, or you would not have a regularizer that you can evaluate for all kinds of hypothesis maps, but you have only this pointwise feedback as in reinforcement learning applications. So you only have for this particular choice of hypothesis or current model parameters, you get the feedback from the clinician, good or bad. So I would
Yeah,
say the difference is in how you implement this regularization term.
yeah. So it's like, yeah, it's like learning the regularization part and then optimizing for that
Yes.
found regularization term that is like the optimization problem that we're solving. So
Yeah.
it's like a kind of an interactive
Yeah.
online, I think,
Yeah.
way of.
Yeah. It would be essentially an online variant of this approach.
Yes, yes.
So similar to the relation between linear regression least squares and online learning, online learning of a linear model,
Yeah.
which is called online gradient descent or something like this. Uh, so I would see the difference in how we get this, how we evaluate the interpretability of a hypothesis, either via this a discrepancy with a pre-trained model, or on the fly as we do predictions by getting feedback from a human, from a clinician. In this case, the human knowledge enters via this regularization term.
Yes, exactly.
Example via the which features we pick for training the simple model, or which patients we consider in the same stage or class.
Mhm.
Yes. But if you have references for this reinforcement guided clinical grounded machine learning, please share with me.
Yes, okay. Like especially for this setting or like this kind of application, I don't know, but like generally in machine learning terms, I have references that I can share.
Yeah.
Just I'd like to add, Mahsa mentioned to a signal that will send by the end user to the machine, and those signals can help the machine be more improve their results, right?
Hmm.
In that case, there's an interaction between machine and end user,
Hmm.
and the machine should get some signals from the end user. In that case, it helps to be improved.
It can, I think it can help improve the, yes, interpretability part.
Yes.
Yes. Because we're learning the interpretable part by human feedback, and that is where human feedback is valuable, because what we care about aligning with is like the human, which is like the clinicals in this case, for instance. And like for instance in these papers there are different aspects that humans have been able, like the scientist has been able to find out, that are very important in finding out about certain disease and so on. But at the same time, we can like find out maybe a combination of those features by interacting with them somehow, or some other form of um, yeah, some other forms of valuable result. But then it will also be important to figure out what they mean. So maybe it's like alignment, and yeah, then what they mean really, we need again a clinical person to recognize what they are, I think.
Yeah, I mean this is a slow loop, so to say, a slow loop how we bring in domain knowledge, and this loop goes via publications in clinical journals.
Right.
And of course, in the long run, one can think of making this loop faster. So every clinician who does a new diagnosis or a new administers a new treatment gives a bit of feedback. So we have a big system which is online learning the best interpretable predictive model for strokes.
Yeah.
Okay. Any other questions or comments?
I would like to ask a question, which
Yes.
I'm not sure if it makes sense, but let's say. So in terms of this alpha value, we saw in the graph that it was like different values were tested, like it was increased. Um, how to ask this? So, is there any hint, or like, does it make sense to see what would be an optimal value, or that it's up to 2 was tested? Could it
Very good. Very
have
good.
gone
So,
further? And
yeah, yeah. So I forgot to make a slide, future directions. This is one to develop some theory for example, what is the optimal value of alpha?
okay.
How do we choose the regularizer in different applications? What's the best way? Is it useful, or what's the best alpha for a specific choice of key features? All these interactions between these different hyperparameters should be studied. So we are just scratching the surface here and have just some encouraging first numerical experiments. But the next step would then be to, for example, study theoretically how much does this regularizer help to prevent overfitting? Like this is something called bounding the generalization error. Uh, so some first ideas would be to try to understand how much does this regularization term reduce the variability of the predictions, or how much more does it make it stable? So stability of this learning algorithm. Can interpretability also enforce or ensure stability? And stability turns out also to be crucial to avoid overfitting. But yeah, this is completely open at the moment. We don't know what the optimal alpha is for a specific application. Any other questions or comments?
Yeah, thanks a lot for the interesting talk. Unfortunately, I had a bit of technical problems. I didn't get everything. I think I will rewatch it. Can you also share the the slides and maybe also the master thesis?
Yes, the master thesis will be published soon, or is already published soon, but I will make sure to share a link. And I will put also the slides online and share a link.
All right, thank you.
Okay. Yes, so if there are no other questions or comments, then I would close this affiliate meetup. We will meet again, same time, same location, in 2 weeks, where you will hear about using stories for teaching language.